10 December 2025. Today I'm revising diameter of binary tree. Yesterday I did three tree versions. So this is a follow-up, maybe. Given the root of a binary tree, return the length of the diameter of the tree. The diameter of a binary tree is the length of the longest path between any two nodes in a tree. The path may or may not pass through the node. The length of a path between two nodes is represented by the number of edges between them. Again, just one example. Sometimes I find good examples in the discussion. Now, yeah, so the diameter is the longest path between any two nodes in the tree. And since we are not given two arbitrary nodes, we just have to return the longest path in the tree, which is 1, 2, 3. From 3 to 4, this is the longest path, or 3, 1, 2, 5. Okay. So for this problem, I'll be using depth first search, and it will be similar process, like we similar way we calculate the height of the tree, or when we check how many levels there are in the tree. So I'm going to check if the base condition, if it is null, then 0 height. Test case. One. Yep. Well, if there is only one, yeah, if there is only one node, then there is no height. There is no diameter, because an edge defines a path. If there is an edge between two nodes, then it counts as one. So if there is no node, or if there is only one node, then the result will be 0. So we'll calculate the diameter of binary tree. Checking the left subtree, right diameter of binary tree, checking the right subtree. Okay, when we are at this level, or when we reach a null, there is no level below 4, so we will hit a null there, and that's when it will return 0. So when root is 4, its left will be 0 and right will be 0. And it will return its own result up to 2, this here. So at this level, we should get 1. 2's left should be 1. Then int height. Because 4 will send its height up to its parent. Yeah, math, whatever is greater or right plus 1, return height. So far good. So far good. But this is not the program to calculate the height, diameter. This is the program to calculate the height. Okay, now let's see what is our code doing. Okay, at this level, left should be equal to 1. No, it's 0, and this is 0. So 4's left is 0, 4's right it's 0, and 4 is returning its own height. Shouldn't we return 0 or 1? No, I think we're right. 2 will get 1 as left and 1 as right. And 1 will get 2 as left and 1 as right, indicating paths. We need to add these two paths. We need to add left and right. And check if we check whichever is the diameter. Yeah, we're going to define it in global scope. This is the recursive function. Diameter 0. And we will check diameter equals left plus right at max. Get max of diameter or left plus right. And because we want to use diameter as a result, the diameter. Mm, right. Want to return. So we want to calculate the diameter. Diameter root, and we will return diameter. Zero zero. But we will return height. So 1. Let's see. That's fine. Since it's a depth first search, the time complexity will be linear. Time complexity is linear because we are visiting each node in the tree, and because we are using recursion, space complexity is also linear. We are not storing any type of data. We're not making use of any type of array, but the space that recursion call stack takes in the memory is the only extra space this program makes. So yeah, linear. Linear solution. So we 11 September last time. The first search. We see the Kotlin solution. The first search. I like Kotlin because of the syntax sugar. Tail trick. Okay. What's tail trick? I don't know about this thing. Tail trick. Kotlin is very fancy language. Yeah, we're doing the same thing. So I want to see there's some syntax sugaring. Stack. Okay, that's breadth first search. Okay, we need a hash map for this. A root stack. It's a stack of pair of node and whether it's processed. Okay, we have to keep track of the nodes we have been to. Stack for usually we use Q. Depth. Yeah. By the root to false. it be false. Okay, I will try this with Kotlin. My plan is to complete the blind. Is it blind? Is it grind 75 question list? I'm almost done. I'm just doing the revision part, and then I will do these questions with Kotlin. Okay. Next question. Container with most water. You're given an integer array height of length n. There are n vertical lines drawn such that two endpoints of ith line are you're given an integer array of at n height. This is an array n vertical lines drawn such that two endpoints of the ith line n vertical lines okay, so each number represents a vertical line. Ith line. So this is zeroth line. This is zeroth line. First line. Two endpoints of the ith line is ith 0 and height I. Okay, represent the height. So endpoints of this line are 0, 0, 0, 0, 0, 1. 1, 0, 1, 8. Find two lines that, together with x-axis, form a container such that the container contains the most water. Return the maximum amount of water a container can store. Notice that you may not slant the container. What does slant mean? Like I can't slope. Does slant mean slope? Okay, I have find most water. Okay, imagine these lines as the boundary of a container. and we just have to find the area. The largest area. This is a rectangle. So length multiply breadth. We have the length and we know the breadth. It's constant. Okay. I n 0. I n 0. 1 and 0. 2 and 0. Uh, this is a two-pointer problem, I'm sure. Forget about the water. We just have to find the largest area, which means finding the largest rectangle. Uh, Imagine this. The first two lines. This this can be a rectangle. You can just find this area, and we can say uh, we can keep a max variable. Then we can start here. So I'll keep a pointer, 0, b pointer, no, left, right, height, length, -1. You just have to make sure that left pointer is smaller than the right. Now we need, for area we need length multiply breadth. And the first time I did this question, I did not know the area, how to calculate the area. So yeah, that happens. Length, breadth. Well, breadth. We know the length. We know the length. Length is given. We need to calculate breadth. So we'll take a minimum of both heights. Math minimum of height at left and height at right. Breadth is um, left minus 0, 1. Left will be always smaller. So right. So 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 and 1. 0, 1, 2, 3, 4, 5, 6, 7, 8. So 8 minus 1. Right minus left. Exactly. The area is result 0 and result math menu result area and let's just return the result. This way we are checking. We're calculating every possible area and only keeping the largest area. That's one. And I forgot to increment my pointers. or to move my pointers. Right minus. Okay. 24. Why 24? Let's see. 7. Result was 8, 18, 24, 24. Okay, we're starting from here and here. We're calculating. So that left is 0, right is 8. So breadth is 8. Length is 1. Area is 8. And then we move our pointers. Left is 1, right is... I know the way I'm moving my pointers is wrong. Because when I move my pointers, right will get here. I don't want right to move. If the if the if the next height is greater, only then move. It's this condition. So for here, left is at 0, but the first index is greater. So left will move here. In this case, its next height is not greater than itself. So R will not move. Left if height left left plus 1. Then we move left if height right is smaller than next height minus 1, then we move right. No, it didn't work. Equal, equal. Okay, these are at least we are getting the answer. We just need to find a way to get out of this loop. We are getting stuck on. Hmm, we are getting, yeah, we are here because the next pairing of the solution is can be wrong if, for example, if this was a if there was a height here which was greater than the first index, so this pole, then we would use this pole to calculate the area, not this one. So we should find a way to move the pointers to so the right now the condition is only move the pointer if the next pointer is greater or equal to the current, if the current height. Left pointer moved one step, or right pointer did not move any step. We need two extra variables. L R initially set to right and left and right. So while left and right, left and right will move. So if the height at left is smaller than the height at L right, just ensure that L is not equal to height left, and the left becomes L, right becomes R, and right is not equal to right. Okay. 80, 18. System dot out dot print 9 result. 18, 18, 18, 18, 18. Left and right. Right. Why did right move first? So the condition was right should not be equal to R, and if the height at R, if the at this index is smaller than the, here it is not smaller. So why did it move? Hmm? Oh, right, 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 right. Yeah. Expected 4. We passed quite test cases. Expected answer was 4. 3 minus 1, 2. 2 multiply 3 is 6. 3 minus 2, and the minimum. Okay, this is not the answer. Then we move, because the next height is greater. We move the left pointer to here too. The next height is greater. 4 minus 2, 2, 2 to the 4. How did it bring 3? How did it bring 3? 0, 3, 0, 1, 3, 0. Oh. Okay, did we hit this condition? Did we break the loop? Did we break the loop accidentally? I think we did. Yeah, the correct heights are at these indexes. But no, we did not break the loop. It just failed to calculate the height, calculate the area. Zero, 1, and 2. Right. But at this level, when we got here, when the left became 1 and right became 2, I think our left and right still had old values. They still had 0 and 3. What is that? All right. Because when we got here, our these values were still holding the old values, and it was, and this condition would bring our left and right to current values, and we increment these. But as soon as we do, we break out of the loop. So this code never got to run with updated values. Still 3. I think there's no point in making it equal because by the time they got there, they passed each other. Uh, yeah, they passed each other. Clearly not they. Mm, not a good solution. Okay, I'll give myself 2 more minutes. If I can find it out, if I'm not able to, then I will look at the solution. Just making sure I didn't put a typo in it. Do we really have to do this? I, I think we're just fine with left and right. Left, right. Uh, don't need this. Don't need this. Left, right. -1, +1. This is still not get past here. Mm. Mm. Last time we passed more cases. Okay. Let's check it out. What did we do wrong? Next area. Okay. Alright, we are comparing them with each other, not with their next values. At least we got this part right. By luck. It's just a small tweak and it doesn't matter. Smaller than or equal to. But why does it work? When we are here, when we're at 0th index, we check if current height, which is 1, is smaller than height at the right end, which is 7. Yes, then we move the left pointer and it will not go to else case, and we calculate the area, and then we check if 8 is smaller than 7. No, then we move the 7. Else case. Now, now right is here, left is here. We only move the right pointer when it's smaller than the. We only move the left pointer when it's smaller than the right pointer, right height. Okay, fair. Okay. I think I need to learn to do it in brute force way. Yeah, current complexity is linear. Uh, if you simulate the problem, it will be quadratic squared n squared. I need to learn. I just need to simulate this problem. So two loops, because we are literally checking each element with every other element. We will check 1 with all these elements, then we'll check 8 with all these heights. Yeah, it's okay. I just have time for this last one. Min stack. Design a stack that supports push, pop, top, and retrieving the minimum element in constant time. Implement a stack class that should support all these operations in constant time. So we initialize a stack, we push 2 onto our stack, we push 0, and then we push 3. When we ask for minimum element, it should get us 3. When we pop, it should pop. Well, stack is what? Last in, first out. So this element came last in our stack, so it should pop 3 minus 3. Then if we check the top, guess the top element of the stack. Okay. Top will return the recently pushed element. Get minus will return the get minimum will return the minimum element from the stack. So yeah, all this and these three are easy to implement. Get minimum in constant time. There was a picture here somewhere. Yeah. And so Dave constructed a megaphone using only some string, a squirrel, and a megaphone. And we will construct our minimum stack with 2 stacks. Uh, this is our A stack and B stack. As soon as any element gets pushed, so like push minus 2, push 0, push minus 3. We get the minimum. We can keep track of the minimum element with minus 3. Once 3 gets popped off, we are left with 0 and minus 2. And get minimum on this stack. Well, do we even need 2 stacks? We don't need 2 stacks. Stack integer stack new stack and minimum element. Well, let's take our own examples. We push 1 and then we push 2 and then we push 3, 4, 5. speak. Pop. Can we keep up min stack? Methods pop top min operation will always be called a non-empty. Okay. Initially the both stacks will be empty. So any element that gets pushed is the minimum element. But after that, so this key, you can check if we can maintain a current min if value is smaller than current min or simply math min current min and value we want to push well. How do we can get the next? I think we need two stacks. No, I'm very confused. Like, if we have, let us brainstorm. initially, okay, as soon as any new value comes in, we check. Okay, if this value is smaller than our previously calculated value, if it is, then we set our new minimum. But once, uh, and as soon as this someone calls that minimum, we return that value. If the element gets popped from the stack, from our main stack, then we need to check if that popped value was the minimum value, because then we would need to calculate a new minimum. For example, here -3 was the minimum, then we popped off that element, which just happened to be the last element on the stack. And if the next call requests get minimum again, um, I don't know how we will give them that. Minus, is it even possible to do it in constant time? Hmm. Consider each node in the stack having a minimum value. Each node in the stack having a minimum value. Priority queue. Priority queue. Oh yeah, we could use priority queue. Last time I solved it with stack, so I thought the stack would be the only valid way to do it. But yeah, now I'm considering one a priority queue can also be a great option. Just min heap. But I don't know if it supports uh, does adding or removing happen in constant time in priority queue? I don't know. Yeah, the only problem I'm trying to think of is how to make the next value available, next minimum value available as soon as the current minimum value gets popped off. But that is only if the minimum value happened to be the latest element that got pushed onto the stack. Am I too close to the comment? To next minimum. If big is big as minimum element, then okay, find new minimum. Okay, it's still not pop. Value. I have to hurry. I have to hurry. Value. I can just get rid of this element. Okay, this is maintainer stack. Stack integer min stack and is smaller than min if min is not empty. Well, if min is empty, then just push the value. Then not push value if let's say min dot peak is the then you then well, if we set the value, if we push this new minimum onto the stack, and should we pop the last value? Then if we do pop off the last minimum once we find a new one, then what's the point of even keeping a different stack when this minimum element can just do this thing? Yeah, I think okay, I give up. Oh, yeah, we were keeping those stacks. If min is empty or we find a new minimum, we push on to this min stack. Really, is it that simple? Because man, you see, we never pop off things from min stack. Yeah, min, none. What happened? Oh, min take. Mm, What's happening? Get minimum is returning a wrong value. We are opening the things a bit differently here. Okay, with so min dot pop. Yeah. Empty stack exception. Well, this code never got exception. Okay, min is empty, min is min dot weak. Or min dot weak. Greater than or equal to min w. R duplicates allowed. Uh, okay. Then stack push, push, push. Four push operations. Similar elements. So yeah, duplicates are allowed. Pop, pop of this one. Get minimum should get this element. It does that. Okay. And then we pop. Should pop of this one. Get minimum. Get minimum and then pop. Get minimum. This element. Pop the last element by 12. And then get minimum. Then we pop off. Is using math a better way to do this? Nope. Okay, okay, all right, all right. No, 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 because we're doing the same thing here. Wasn't I doing the same thing here? Like, what's the difference between this and this? Here we first pop off the value and then compare that value with but isn't it is this not the same thing? Why is this not the same thing? Maybe I need to debug these cases now. Okay, thanks so much for watching this video. I have done 3 questions today, but I think I need to ex really find out what's really happening here. Or maybe when I rewatch this video, I will just know, you know. Okay, bye bye.